gentlemen, my name is Thomas Kamicek, and I'm now doing the components on problem number 7, cup drum. Just outline of the presentation. The product had a very nice structure. It included, of course, the theoretical approach, the blade vibration of the cup, and of course, so the eigenfrequency of it, the standing waves that are produced inside the cup, as well as the damping and the pitch dropping effect. In his experimental observations, he had a very nice setup, and he could even give us some sound samples to get an idea on what the sound is actually about. He had definitely a very nice method of frequency measurement, and at the end, his comparison, he shows amplitude versus frequency, and he compared his results with the cup above the water and the cup under the water. Well, the good points of the presentation was where that the very distance from the water above or below the water was quite a variation. They even calculated with wavelength, with frequency, and so even they could give us a relation between the pressure, which is deformating the cup, and the amplitude of this sound. The experiments included a different range from between the distance above the water, and even different frequencies, different harmonics. But there are some missing points, in our opinion. They could have actually experiments done with other materials, so the elasticity of the cup could be influenced by this way, and of course, so the eigenfrequency of the cup would have changed, which is a very fundamental fact for this broader effect. There are some measurement errors, and actually we cannot be so sure if the measurement is just has a very big failure or the theory is actually wrong. In these experiments, there were this is called damping through the cup holding, of course. The wave tapping wasn't actually explained. This is a discussion. And the position of the microphone is very important, but we will discuss it later on. Now I want to report the discussion. These are my points.
Okay, so the discussion starts with that point.
What is happening actually if you bang on this ground now? What is happening?
Right now, if you tap it like this, with water, there's a combination of the plate frequency as well as a combination of standing waves that exist inside.
Yeah, but how do we get actually? How do we actually get? We have a cup here, and once bang on the cup. How do we get from one impulse actually a harmonic system? How do we get a frequency here just by one impulse? If there's just one impulse, this impulse is running down, maybe coming up again, but how is there a frequency? How is there a wave? How is there something harmonic?
Alright, let me clarify how waves are formed. So, firstly, let's explain how thin plates are formed, which is rather pretty conspicuous. If the plate is initially in its flat position, but because this thin plate must also have some elasticity modulus and a Young's modulus, if it's deformed to a certain extent, when an external force is applied, and this external force disappears, it's a damping oscillatory system, and you probably also know that.
So you would say that the frequency which produces the waves is dependent on the eigenfrequency of the cup.
Could you please explain for the audience what eigenfrequencies
has some kind of eigenfrequency. If you give an impulse to something, it oscillates with its own eigenfrequency.
You mean natural frequencies?
Yeah.
Alright, yeah, exactly. For thin places, for cases of thin plates, I think there's a difference in the uses of terminology here. But the eigenfrequencies that mainly you're discussing right now are the thin plate vibrational fundamental frequencies that I've explained in my presentation. So yes, thanks for that point.
And what do you think if there's water now here?
Okay.
What is the critical parameter for the reflection for the wave backwards?
Alright. The reason why...
If they are standing waves, they must somehow get back. Why don't they just, and the cup, if we have nothing on the cup, why don't they just get through the cup and fall over there?
Alright, let me show you a picture here. He asked me the question of whether I consider the effects of the reflected sound. Now, if you want to consider a reflected sound, we need to firstly understand the basic principle of why reflection occurs. And the reason is, as you probably also know, is because of the difference in the acoustic impedance of the sound propagating underneath water when it's above water. In the case of when the cup is held above water but close to the surface, yes indeed there will be an acoustic difference existing there, but also there will be some forms of sound that transgress into the regions of water. There will be some reflected. But in order to analyze the cases of reflecting sounds, firstly, it's not a dominant sound because the standing waves are the main points.
I have one point. If you just come back again, what has changed actually if we hit the cup right here, in the middle here?
Changes with different hitting locations.
Let's have a look.
Alright, I can explain that with my theory as well.
Because the elasticity and the whole materials of the cup.
Right. If you vary the hitting location, what happens is that in the thin vibrational wave equation that I've shown before, I told you that the solutions would be in the form of a root of the Bessel function. Now, if you hit it in other locations other than the exact centrifugal axis, what happens is that other mode frequencies occur from different solutions of the Bessel function. When you hit it in the middle, that's the fundamental frequency that I defined.
Two other things. You mentioned this overvised correction that the wavelength actually is a bit longer than the length.
Yes, it is. That's the incorrect.
What's actually your opinion about if we just get near to the surface within this overvised correction? The wavelength should actually be shortened, isn't it?
The wavelength should be increased because sound velocity increases.
If we just come nearer, and the wavelength actually is actually longer than this, and now we approach the surface, the wavelength should actually be shortened because there's no place for it.
Alright. The reason why you think that there is no place for it, I think, is because you believe that this wavelength, this sound propagation, 100% reflects off the surface. But in reality, that's not really the case. There are proportions of sound that reflect, but there are also proportions of sound that transgress.
Can you maybe explain this nearer?
Huh?
Can you maybe explain this nearer? To make everybody understand?
Yes. The pitch dropping effect that I explained is when a sound propagates from different materials and different mediums, there's a difference in the acoustic impedance, which you can easily understand as a form of resistance to an electric current. Now, because of this difference in the acoustic impedance, there are some portions of that initial sound propagation that reflect off the surface, but some actually transgress through it. Now, if you look at the components that transgress through it, the wavelength increases, and that's why the pitch drops.
What actually, the crucial points in your measurement, actually, did you have some system or some reproducible way of hitting the drum?
Alright, I'll show you how I...
A very crucial point.
Alright, so the tapping method is firstly composing of a tapping machine that I built out of a science kit. And this is powered by a power amplifier and a constant speed velocity motor. So the frequency of the tapping is kept at constant with the same force. The location was exactly in the centrifugal axis I calculated with measurements.
Okay, well, more points. How can you explain or how do you calculate the frequency of water? First, you have something in water, and then oscillated, you have, of course, something, vibrations or oscillations in the water. If you calculate this in some way,
alright.
What would you say?
The oscillations in water occur both when the cup is substantially close enough to the water surface, and this is because of the fact that the water wave, sound propagation, and the pressure differences also hit the water surface. But also, the water vibrations get even bigger when it's submerged underwater, and that's also because of the sound propagation, but also the axial vibrations of the side wall. And the numerical calculations for that would be quite difficult, so that those are some of the prospects of the experiment.
Yeah, and actually we have, of course, we have air in it.
Can you repeat that?
We have air in this cup, of course.
Okay.
Okay. And of course the speed of the sound is very important.
Yes, the speed of the sound is important.
What are the important parameters for the speed of sound?
Alright, the main parameters probably for speed of sound is firstly humidity, and secondly it's the temperature inside the room. There are both numerical calculations to how the velocity of the sound changes.
Yeah, and actually the adiabatic index, isn't it?
Adiabatic index.
Adiabatic index, of course, defined as the degrees of freedom plus 2 by of freedom plus 2.
Can you explain how that's correlated to the initial velocity equation, which is supposed to be the square of the bulk modulus divided by the density of the material?
Also the speed?
What? Bulk modulus. So this is the equation for sound. Can you please explain, for better discussion, how this correlates to either the density or the bulk modulus so that the jury can understand how this has changed?
I would say that the velocity of sound is the root of the emphatic index times pressure divided by density.
Right. So perhaps these two constants are the same concepts that we're trying to use. All right.
Pressure is not really a constant, but
okay.
Let's say so in a moment. But actually, you mentioned once that the delta frequency, the difference of frequency is zero. What you meant actually about this? Actually,
the delta frequency
because just letting on proof this. You mentioned in your presentation that delta F is zero.
Delta F is zero for the case when the cup is submerged underwater. So what I was meaning for equations of delta F equals zero for standing waves was that it changes when it's above water but smaller than the difference of 0.61 R. But if it's submerged underwater, because there's an insignificant amount of the influx of water creating a pressure.
Actually, if you push the cup
yes.
far into the water, of course you have a different pressure. Haven't we?
Yes, the pressure is gradually increased.
Just give us a short sketch of your experiment. Sketch it.
Okay. For when it's submerged or for when it's
on the roll.
Okay.
Doing the water surface and so on.
Perhaps it's better to show you a picture.
Give me a sketch. It's good. Very fast, please.
All right. So
we're running out of time.
Sketch.
Yeah, please.
Consists of a cup and a sound sensor for underwater, placed like so, and a water cavity like so.
Yeah, and there's a ball in the cup.
Huh?
There's the ball in the cup.
The water only comes in an insignificant amount, like about this much, and this increase in the height is very minimum.
But for wavelength, this is quite a big value, isn't it?
It's not comparatively L. I actually have numerical calculations for how much the water actually comes into the cup.
Yeah, well, let's go on. This wasn't my question, but please let's go on. And actually, if we have just a bigger pressure here, and the gas is compromised, isn't it?
Yes.
Yeah. So actually, we would have a bigger pressure in the gas. How is this influence on this velocity of this sound?
Okay. There is a pressure term in the change in the sound velocity. I completely agree with that. But if you see that minimum changes in the pressure, which I calculated in this cup to be about 0.1 kilopascals.
The pressure influences the speed of sound.
The pressure influences, but it's insignificant because there's only a change that I calculated to be about 0.1 kilopascals. And in terms of affecting sound velocity,
it has influence. Okay,
very small.
Actually, it's not the task test in terms of sound. What is sound actually? Sound is more than just amplitude and frequency.
Yes, it is.
Yeah, of course. And what are the other characteristics or qualities of sound?
There may be characteristics such as the differences between a violin and a viola, which is the timbre of the sound, some of the sound patterns, and there are many other components such as loudness.
Actually, there has to be some intensity and some pressure. And this pressure actually doesn't have an influence on the pressure of the sound.
It influences perhaps at a very, very minimum scale, but in terms of the major dominant frequencies, very little
didn't calculate at all.
Yes, I actually calculated the increase in the pressure. That was only 0.1 kilopascals.
That's actually your measurement errors are quite big. Actually, I'm so sure if your theory is correct or your experiments are fundamentally wrong.
Which errors are you particularly talking about?
There was some. You have those numbers on the slide, so I can't actually remember. But there were some graphs, and the errors didn't reach the graph in the theoretical approach.
Some of the data points actually quite well matched the experiment. Some of the points that did not match, I explained I had explanations for why some of the errors existed. For example, the standing wave frequencies below water, you can see that the error bars quite well overlap with the theoretical data here. For some of the points, such as the standing wave frequencies, there may be some of the points that exist at a discrepancy. And if these are the points you're talking about...
It's quite bad, in fact. But, actually there's a problem. I think that there are many other qualities of sound that could be...
Right.
But actually, I hope we could improve your presentation a bit, because that's actually the purpose of this
Thank you very much.
Okay, thank you very much for the discussion.
So welcome together. May I have some questions to the reporter and the opponent? First, the surface tension. Will there be an influence of surface tension if the cup is nearly above or nearly below the water surface? First to the reporter.
I believe there may be the influence of surface tension in terms of creating what types of modes of waves are created on the water surface. But in terms of influences being the standing waves or the major thin plate vibrations, the effects of the what you just said would be nominal.
Okay, what did the opponent say? Is there a clear on the surface definition?
Yeah, actually it's quite hard because the capillarity force actually trying to catch the beaker actually hasn't really reached the surface. So, but actually you can say if there's no connection between the air outside and the air between, actually you can say something like this.
Okay, thank you. Then to go on to the reporter,
Right.
what will the overtones of your frequency be?
Right. For standing waves in a one-end closed cylindrical cavity, the overtones are mostly the third harmonics and the fifth harmonics, which are about approximately 3 times the size of the fundamental frequencies.
Okay, are the overtones harmonic?
The overtones are... Can you repeat your question?
Are they harmonic?
Yes, they are.
Okay, what do you think about this?
Harmonics? Sorry?
Is the overtone of the frequency harmonic? So is it a harmonical oscillation?
Actually, yeah, the plate of the beaker is also...
Yeah, but the whole system.
The whole system always is for stand, but harmonic.
Okay.
There might be differences in plate vibration. I was only talking about the standing waves.
Okay, then to another influence. If the cup is below the water surface, then there will be some vibrations on the water surface, and there will be may also be some drops coming out of the water and attached to the side walls. Will this have an effect to the reporter?
My experimentation was mainly used to control the sidewall vibration. And so, because the sidewall vibration isn't really a dominant factor in generating sound, I think the water attached to the sidewalls will have an infinitesimal amount of influence.
Okay, thank you. Then to your measurements. You did the fast Fourier transformation, as I've seen.
Yes.
Did you use which type of the Fourier analysis? Did you use an absolute value of the complex number or the real part?
The absolute value.
The absolute value, okay. Then, how good is your reproducibility of the measurements?
Seeing from, firstly for cups with different length, you can see that some of the air bars are actually contained inside the points. For many of the points, that was the case. So the phenomenon would be quite reproducible in my case.
Okay, thank you for the questions.
Thank you very much. So